So I'm Julian Hyde. I work for Hortonworks. I come from a variety of backgrounds, SQL relational databases. I started my career at Oracle. I've done OLAP over at Mondrian, the leading open source OLAP engine. I've been involved in streaming for probably about 10 years. I was the founding chief architect of a company called SQL Stream, which combined SQL and streaming. And what I'm talking about today is an effort to bring SQL and streaming together and see whether it's possible and build some consensus about what SQL extensions would look like to solve streaming problems. So there's a variety of streaming data sources, both within the data center and Hadoop and outside. There's a lot of talk recently about Internet of Things devices, sensors, data coming from your phone and other kinds of sensors. There are also streaming data sources in the data center. Log files are an inherently streaming data source. At least they're generated by web servers and ongoing processes in the data center, and they need to be monitored. Databases, the change data capture, the transaction log of a database is inherently streaming. So the challenge is to bring all of these data sources together in a convenient way. So what drives this? I would argue that the move to streaming, or whether you want to process data as streaming data, as opposed to storing it as stored data, historical data, data at rest, is cost or value. Some data has pretty much the same value, whether it's 1 minute old or 3 years old, but some data has a lot greater value if you act on it, if you're aware of it, can process it with a short space of time. So some data has kind of an exponentially decreasing value. So for example, if you're doing high-frequency stock trading, you want today's bids and asks for a particular stock rather than yesterday's. In fact, you want the data from 1 millisecond ago. And so the value of that data, measured in dollars per gigabyte, if the data is valuable, then it makes sense to be storing it in memory. And older data, you probably want it stored on disk, perhaps at a lower replication level and so forth. So as data cools down, as it becomes less valuable, as it becomes updated less often, it tends to migrate from memory to disk, and that's simply kind of a matter of cost. And so old data will be, and less valuable data will be available only on disk. But I would argue that data, that if you can combine the hot recent data with the old data, it's actually more valuable than each of them on their own. And kind of to add to that point, somebody once told me that the only useful metric is a ratio. It's not interesting to know that a stock is trading at $30 today. You really want to know whether that's twice its historical value over the last 6 months or half of it. It's not interesting that a particular web server is processing 1,000 requests per second because, what was it processing yesterday? So the historical data allows you to automatically normalize and put stuff in context at the very least. So it's kind of a well-known result or theorem that streams and databases are duals of each other. That's to say, a database is nothing more than a cache of all of the data that flowed into it. It's the sum of the inserts and updates and deletes that have been put into that database. And especially if it's an append-only database, which a lot of databases are these days, it's the sum of all of the inserts that have gone into it. So if you think of those inserts as a stream, the database is just the cache of the stream. And likewise, the stream is just the change data capture of the database. Now, this is kind of ignoring the important question of where is the data actually stored. But in terms of information content, the stream and the database have the same information content. data is really valuable. Data's the new oil. You know, there are a lot of enterprises that think of themselves as data companies. And so, in fact, it's the reason why you guys are here, I imagine, is to capitalize, is to extract the maximum value from the data in the organization. So treating streaming data and data at rest as treating all of it as data, as opposed to having one department in the company dealing with streaming data, you know, the message-oriented middleware people dealing with that data, and the database people or the Hadoop people dealing with the historical data just doesn't make sense. We need to try and bring them together. So SQL, never bet against SQL. It's been around for a really long time, and to a lot of people, all it is an API to your database. And following that logic, if it's just an API, then you can build another API, and who cares whether it's a SQL-like language or whether it's actually SQL. But the benefits of SQL are kind of underneath the water. They're below the tip of the iceberg. SQL is a declarative language, which means you ask for what you want, and the system figures out how to get it. And in order to do that, any SQL system has to have some form of query optimizer. If you do a simple query, you know, select star from employees, join departments, you don't want the system to do a Cartesian product of all of the employees and departments and filter out the ones who happen to have the same department number. You actually want it to use indexes or some, you know, merge join or some intelligent way of accessing the data. So you take that as a given in a SQL system, that there's an optimizer. In order to build that optimizer, you have to have, well, the people building the DBMS use a mathematically sound language, relational algebra, to represent that. And then once you've got that, it allows you to do things like you, the database administrator, can reorganize the data in your database. You can add indexes, you can repartition the data, you can move to a different physical storage format, and your application still works. Your application developers don't even notice, except hopefully the application runs faster. And it's standardized, which means you can run tools such as Tableau on top of your SQL database, and it doesn't even matter which product you're using. You can use the standard tools right out of the box. These are all really great things. So these are all good reasons why we should be looking to if possible, bring SQL to manage streaming data. SQL doesn't imply a particular standard workload. In fact, there's a variety of data workloads. And you know, let's not even talk about whether the data is in a database or in a streaming system such as Kafka. Let's just look at it from the CIO's point of view, who doesn't really care about where the data is stored. These are the kind of things that you would want to do with data. And when you actually implement it in a physical system, of course, it needs a very different kind of system. So batch operations taking many hours to process data. Transaction processing where you want to update, you know, 1 or 2 records at a time, perhaps with isolation levels. Looking at records, you know, looking up a customer's information when they hit your website. Searching for documents or records based on criteria. Interactive exploration, interactive OLAP, where you're querying large amounts of data, but the user wants the results back in seconds. Adding to this kind of the continuous use cases like complex event processing, where the data is flowing through the system, but you're looking at patterns. But maybe a pattern of accesses where someone is trying to a denial of service attack, or someone is trying to break into your enterprise. So particular patterns of events can indicate that that's happening, and you want real-time results out. I should say the word real-time is overused. You want continuous results out. As soon as the pattern has been recognized, you want it pushing to you, sending you an alert in some way. And then continuous load, so kind of doing the ETL, but rather than doing it for 2 hours every night, doing it continuously so the data is flowing out of the operational system into the analytic system, the historical system. So lots of different workloads. Just about every one of those needs a specialized engine, but wouldn't it be nice if we can govern this data and address it using the same language? So I'm the VP of Apache Calcite, which is a query optimization framework. It's part of Apache. It's used in Hive and Drill and a variety of other projects and products. But why I'm here today is I'm trying to build a consensus among open source communities and also vendors about the direction that SQL should be going in, because I strongly believe that SQL is a good language for doing streaming in. So I don't want people to invent SQL-like languages. We've all had enough of those. And the key technologies, as it happens, are open source. We've done a lot of work on this in Calcite, but mainly I'm interested in consensus. I don't really care whether you use Calcite to implement streaming SQL, as long as your streaming SQL looks very, very similar to the streaming SQL I'm proposing or that we come up with together. And we've done some work on this already. Several projects are using, we have initial support for streaming SQL in Calcite, and several Apache projects are building streaming SQL using this. So Samza, Stormflink, I'm talking to the Apache Beam folks and the Apache Apex folks. And we also have non-streaming adapters for a variety of projects and products. So let's look at some simple queries. So the query at the top is we don't have a good word for this. Sometimes I call it a relational query. It's a traditional non-streaming query. So you're querying a table called products and finding all products whose unit price is less than 20, easy. So they cost less than $20 each. The bottom one is a streaming query. We're looking at an orders stream and saying, give me a stream of orders, orders which have more than 1,000 units sold. So the top one will execute the query, take 2 seconds or whatever, come back, and then finish. The bottom one will execute continuously. So you might get a record back, and then there might not be another record for 5 seconds, and then another record might occur, and you're reading from an infinite stream. You can run this using JDBC if you like, but your JDBC program will never finish. It will just print out new stuff onto the screen. Or perhaps you're not using JDBC, perhaps it's lying somewhere between a couple of message brokers, maybe reading from one Kafka topic and writing to another Kafka topic. It runs continuously and never terminates. Okay, so actually I lied. Orders is not a stream. It's a stream and a table, because it makes sense that you want to access, sometimes you want a stream of new orders, and sometimes you'll want to look at historical orders. So in these queries, which, well, it's variations of the one on the previous slide, the top one, I'm asking for historical orders. I'm implicitly asking for all orders that I've received up till now, which had more than 1,000 units, which implies I'm going to look on disk for them somewhere, or rather the system is. As specifier of this streaming SQL language, I don't really care where it gets it from, as long as it knows where to get it. So this is asking for all of the old orders. The bottom one, the only difference is the stream keyword. And what I'm saying is I want a stream of all of the orders from now onwards, which have the same criteria. And that data is probably coming off of Kafka or Adonai or who knows where. Again, it's an implementation detail of where the data is actually coming from. But the nice thing is that the queries look incredibly similar for those two things. And you're querying the same object in your data dictionary. Orders represents both things. It's how you use it in the query which determines whether it uses historical data or the streaming data. So why have we gone to all this effort to make orders both a stream and a table? So we can do stuff like this, combining the past and the future. So select stream. So I'm asking for a streaming query. And I've got one reference to orders, which you can kind of think of as a stream. So from the order stream, from all of the incoming orders, I want to find all orders that are larger than the average size of orders for that product over the last year. So you can think of the second part of it as a query to the historical orders table. But actually, as time rolls forward, I might start this query at 10 a.m. By 11 a.m., data that has arrived in that hour since has now rolled from the stream into the table and is now counting in the 1 year moving average. So the system is kind of doing this juggling between data which is arriving and then moving into the old part of into the historical system. So if I try and run this, and it so happens that the database administrator has not defined a history table to put this historic data in. If the database administrator has decided that orders is only going to be a stream and not a table, that's fine. You'll just get you'll get an error when you try and execute the query. It says, I don't know where to get the historical orders from. And in a regular database, of course, the streaming aspect isn't there. So orders is just a table. So it's up to you when you're designing your database whether you want streaming or historical or both. Okay, so quite a lot of work has been done on semantics of streaming queries in academia. Around 10 years ago, actually. This stuff is older than it is. Well, people have been looking at this for quite a while. And I'm simplifying the academic work an awful lot, but I boil it down to this. If you want a semantic, kind of well-founded mathematical semantics for a streaming query, you just say, well, the semantics of the stream, applying to the stream, is the same as if I take all of the data out of the stream and I wait until kingdom come, I wait till the end of time, put all the data from the stream into a table, and execute a regular SQL query on that table, I should get the same results as if I execute the query on the stream. That's a pretty reasonable semantic. It means we don't have to define what a where clause means applied to streams. It doesn't mean, we don't have to define what group by and subqueries and so forth mean. Now, obviously, some of those queries may not be possible. The system may say, I can't execute that query in a streaming manner. And there's some examples to come up. But, and also, the system may be able to produce earlier results. The number of orders between 10 a.m. and 11 a.m. is 27. And then at 2:30, another order arrives late. And maybe the system says, oh, I was wrong, it's actually 28. Maybe it restates the results. So that's kind of an asterisk on that definition. If you want results from your system early, you have to be prepared to tolerate initially incorrect results, and the system can restate them. But generally speaking, this replay principle is a nice, simple way of defining what the system should be producing. Another important thing is, in the same way as a SQL query shouldn't produce different results if the data is ordered differently in the table, a streaming query shouldn't produce different results if this message happens to arrive in this Kafka topic 2 seconds before this other record. So the relative arrival time of records shouldn't affect the ultimate result the streaming query produces. Now, the streaming query may produce it in a different order, but in terms of what actually comes out of the stream, it should be the same. This is difficult to implement, but it's as a user of this system, building applications on top of this, this is a very useful property. Okay. Another thing that is, I mentioned earlier, not every streaming query can, not every query can be converted into a streaming query. And I describe this criterion as making progress. So if you go to one of these systems and say, how many orders of product 100, tell me how many orders of product 100 there are, and which implies, from now into the future. Obviously, that's a question that can't be answered because we haven't seen them yet. Now, the system could just sit there, just, flashing cursor, and not tell you an answer until the end of time, but that's not what you want. So the system will give an error and say, well, I'll explain what monotonic means in a minute. But it's basically saying, look, I can't make progress on this query because of the way the data is arriving. Basically, it means, almost certainly it means you haven't included some kind of time-oriented column in your query, in particular in your group by clause. You know, just as in your question, there has to be some kind of time function. So you can't say how many orders of product 100 are there. You can say how many orders of product 100 are there, you know, in the last hour, or what's the daily total of these. If there isn't a time component in the question, then the system can't make progress in a reasonable amount of time. So monotonic means, you know, an ascending value. So the timestamp, whether this is event time or arrival time or processing time, is ascending. It might not be strictly ascending. There might be, you know, a record at 10 o'clock and then another one at 10:15, then another record at 10:05. And that's okay, but it's generally moving upwards. And the system can make use of those properties to figure out when records can be emitted. I'm being kind of fuzzy here. If you look at the talk given by the Apache Beam folks, they have a lot more details in terms of what they call them triggering schemes. They talk about watermarks. So that's kind of lower level semantics about when data comes out of the system. I'm skating over that because I don't want to build too many of those assumptions about what triggering criteria are in terms of the query language. But the general idea is you need to ask queries that are time-oriented, and the system needs to figure out a way of converting those time constraints into, you know, figuring when it can safely output data. So here are some more examples. So a monotonic column is you have committed, you writing into this stream have committed to provide the data in ascending order. So you provide records 1 and 2 and 3 in their ascending order, then you provide record 4, which is out of sequence. If you're going for that scheme, then the system will just say, hey, this is out of sequence, and it'll just drop record 4 because it's out of sequence. Now, that's tough for you. It's good for your consumer because they're getting data in ascending order, and that allows them, it's easier for them to process the data because they know it's guaranteed in ascending order. If you use a more flexible scheme like the watermarks proposed in Apache Beam, then data can arrive out of order, and the system figures out when it's safe to, for example, emit the total for the 10 o'clock to 11 o'clock hour. It may not be 11 o'clock. It may not even be when it sees the first 11 o'clock record. It might be 11:15 when it figures it has a reasonable, it's seen enough data and has enough certainty that the result isn't going to change, that it can produce an initial estimate of the 10 o'clock to 11 o'clock hour. So these are just two policies. More policies are possible. It doesn't, you know, the SQL streaming semantics still hold up. And it's kind of a tuning decision about what policy you would use. And it also depends on what system you're using to run the streaming SQL on. So let's look at some of the operations that you can apply on these. I'm going to run through a kind of catalog of relational algebra, kind of just cross-checking that all of these operations are things that, or almost all of them, are things that are familiar to relational database users because they're in the relational algebra. So it's just interesting to see how they apply to streams and you know, where they're different and what use cases they allow you to solve. So in a database, if you want to do aggregation, there's kind of two ways of doing it. One is using group by, which takes a bunch of records, you know, for example, all the employees that are in the same department and combines them into one record. If you use grouping sets, then all of the employees that are in one department will go into one record, and all the employees that are in the same division will go into a record. So each record contributes to more, basically, subtotals at various levels of aggregation. The same things exist in windowing queries. And then window functions allow you to compute things like moving averages. So for a given record, it has a bunch of related records, like the last 10 trades of a particular stock. So a stock trade occurs at 10:15. You're interested in the last 10 trades of that stock. That's, the same ticker symbol is traded at 10:17. It's going to be looking at a different 10 records. So window functions allow you to do that. All of these things make sense in a streaming system. So let's look at an example of it. So here's a group by query applied to a streaming system. If you just remove the word stream from there, it's a query that would run on a relational database. Actually, it uses an extension function, floor of row time to hour, which says take the row time of the column and round it down to the hour. But I think there's something very similar to this in Postgres, and Drill has something like this. So it's not beyond the realms of possibility. So yeah, at the end of every hour, or when we're pretty sure we've seen all of the data for 10 o'clock to 11 o'clock, we can emit a total for each product ID for the data in that hour. So this 11:05 record, it's now 11:10. We've not reached the 11 till 12. Well, it's 11:55. This record has not, we've not yet completed the hour, so that record is still sitting in a hash table somewhere, waiting to be emitted. So there's a lot of talk from the streaming folks about different, like for example, Apache Flink and Beam, about different window types. And it's been an interesting exercise in taxonomy for me to map these onto SQL constructs. It turns out most of them exist in some way, shape, or form in SQL. My goal was to not extend the SQL language. Well, my goal is to not extend it at all, or as little as possible. And also to retain the kind of look and feel of SQL. The goal is to be able to take tools like Tableau and just run them on top of this system and have them work. So tumbling windows are every time period, like every hour, emit the total for that hour. A hopping window is slightly more general. Every hour emit the total for the last 2 hours, or every hour emit the total for the last 90 minutes. A session window is a much stranger beast in terms of SQL. What you're looking for is contiguous bursts of activity. So if you define a web browser session as a sequence of HTTP requests, each of which is no more than 10 minutes apart, then the access at 10 o'clock, 10:05, 10:08, and then 10:20. The first 3 accesses become one session, and then the 10:20 is the start of a new session because there's a gap of more than 10 minutes. So you can still aggregate the things into sessions. And then lastly, a sliding window, which is what you use the over operator for. Every record has its own kind of cohort of records it's interested in computing the total for. So the trades of that ticker symbol for the last 10 minutes, or the last 1,000 trades of that ticker symbol. So how do these appear in SQL? The tumbling window, you can represent it using the floor function, which you can round down to a particular time period, so you can roll down to a particular hour, a particular minute, particular second, particular day. If you want some more flexibility, you can use the tumble command, which can allow you to use, every 17 minutes emit the total, or every 15 minutes, which is more flexible than trying to round it down to just an hour or a minute or a second. The hopping window has very similar arguments to tumble, except it's got an additional parameter, which is when you emit that total every hour, how many, or every 17 minutes, how much data goes into that. This is, somewhat bending the semantics of the group by clause, because a particular record, if you're using hop, a particular record may actually contribute to the 10 till 11 total and also to the 11 to 12 total. So whereas traditional group by, a record goes into one and only one subtotal. And then session window, we're actually still working on the semantics of that. But that has some even more interesting properties. And you know, for example, will behave differently if you add extra columns into the group by clause. But the interesting thing is the same problems exist when you put that into regular SQL. So it's not a property of the streaming, it's just a property of the way that this sessionization works. We're just facing it here because sessions is obviously a very important thing for streaming data. So sliding windows. This, again, you can remove the word stream, and this is traditional SQL. We'll run on Oracle, DB2, Postgres. So we're computing a couple of moving averages. We are looking at the last hour of data. So we're producing, sorry, not moving averages, moving sums. We're looking at the last hour of data for a particular product. And we're also looking at the last hour of data for all products. So you can compute multiple, and this example doesn't show it, but we could also be looking at the moving sum over the last 2 hours and the last day. So using this, you can compute something like, you know, when the company that looks after your shares sends you something to say, this thing has crossed its moving average, or the 10-day moving average has crossed the 60-day moving average. You can compute that using this in a single SQL query. The pie chart problem, I call it the pie chart problem. I don't think anyone else does, but it's really emphasizes this isn't just about. This encapsulates the problem of making this making this data accessible. So you may have a stream, maybe a Kafka topic or something, of all orders, and you want to run Tableau on top of it, or you want to generate a web page that generates an image, a pie chart. The person writing that web page does not want to have a standing process that's running, taking data off the order stream, putting them into a Java hash table, and continually putting stuff into this hash table and purging it out. They just want to write a web page that generates the pie chart and then returns it. So they want to talk, the person writing that web page wants to talk to what looks like a database. The fact that that database is continually populated by data coming from a stream, it's not their responsibility. They're a web programmer, not a data person. So the challenge is to make it easy for people to generate pie charts and to be able to say, give me the last hour of history of this data, even though it's perhaps still in memory, even though it's perhaps still in Kafka. And you'll notice this query does not have a stream word. Even though it's based on the order stream, the stream word is not there because they want a query they can execute in 3 milliseconds, comes back with the data they need, then they can generate the pie chart. So the solution is, well, the first part of the solution is to be able to represent this in SQL. The second part of the solution is for whichever system implements this to be able to materialize orders over the last hour, perhaps with some hints from the administrator, materialize this stuff in the last hour, so that this web programmer can generate this pie chart. I'm not giving a solution today about how to do that. That's kind of an area where these various streaming systems can innovate. But I strongly believe these streaming systems shouldn't just be looking to produce streaming output. They should also be looking to maintain caches. In the words of the database people, a materialized view of the history of streams. Joins, several ways, several combinations of joins. So join a stream to a table, by which I mean a stream to the history of the stream. In this query, we can imagine that orders is a stream and products is a relatively fixed list of, price list. So you'll maybe interested in orders which are, cost less than half of list price in a particular order. So you're using the products table as a lookup. We have the stream keyword there because we're interested in continuous results. And the implementation would probably do something like caching the product table or parts of the product table. What about if the price list is changing? What about if someone places an order at 9:45 and then at 10 o'clock somebody changes the list price of this, and then at 10:30 maybe the system crashes or someone wants to replay the stream? How do you ensure that the query gives the same result as when you executed it at 10 o'clock? At 9:45. That's a hard problem. You probably need a database with some kind of temporal support. Again, I'm not providing a solution here, but it's a reasonable thing for the user to want, is to be able to see the price list, the state of the price list table as it was when the order was placed, as opposed to what it happens to be now. And sometimes you just don't care. Sometimes it's kind of like isolation levels in databases. Sometimes you actually don't, it's not worth the cost and the performance penalty of maintaining that. Sometimes it's just fine to replay the stream and you get different results. A good system will have those knobs so you can turn down the level of strictness so you can get the performance that you want. And then joining streams to streams. So we're adding a new stream here, shipments. So imagine you receive orders and you receive the order and then they send a carrier pigeon to the warehouse and the warehouse decides to ship this, maybe the same business day or whatever. So the orders and shipment streams represent related business activities, and you're interested in products or orders that ship within an hour of being placed. That is a stream-to-stream join. How do you execute this? The implementation would probably involve 1 or 2 hash tables, caching either the last hour of orders or the last hour of shipments or something like that. Many opportunities to optimize this. Perhaps you partition based on order ID. So an opportunity for the systems to innovate. And always notice, there's a time component to this. All of these queries tend to have a time component. If you just say, find all orders and their corresponding shipments, that's not a query that the system can execute because you're asking to join infinite time to infinite time. If you're tying the 2 times within a 1 hour window, then that is something that can be executed in a streaming fashion. Planning is where Calcite comes in. Calcite, this isn't a streaming query, this is a regular query that's combining data in Splunk and MySQL. The way Calcite works is it converts stuff into relational algebra, and then you can optimize by reordering the relational algebra. The same kind of optimizations can occur on streaming systems. They may be different, but it turns out a lot of the optimizations are very similar. So Calcite is an Apache project, top-level project for almost a year. We have a bunch of adapters, and we're building streaming adapters for, actually this list is out of date. I think we're interested in building streaming adapters for Apache Apex, also known as Data Torrent, and Apache Beam, also known as Google Cloud Data Flow. So I'm going to skip over this in the interest of time. Just to comment that, so this is relational algebra that you'd learn in school, the stuff that every database implements. Streaming algebra, if you read a book on enterprise application integration or enterprise service buses, you've got these kind of concepts. like queues, merging, replaying. It turns out that a lot of these, the mapping between these and these is actually not, they're not as far apart as you'd think. So, and what you're actually producing is a data flow graph, which is very similar to the data flow graph that every database is using to execute. I'm running out of time, so these slides will be posted online, but I've got some remarks about how you can apply query optimization to these. DML is something that makes sense in streams. You can have a streaming insert or a streaming update, applying a stream into a table continuously. And materialized views are kind of an essential part of this in terms of allowing relational queries on streams. So, in summary, the benefits of bringing SQL to streams is that SQL is a very well-designed language, very well-established, has a lot of people that speak it, and it has an immense amount of power to a system and an immense amount of manageability to a system. We're using an Apache process to do this, which means open discussions on mailing lists. So please get involved if this interests you, and your voice will be heard. Everyone's voice is valid and useful. So, yes, time for some, I think I have 3 minutes for questions.
Are there any assumptions about the format of the stream?
The question is, are there any assumptions about the format of the stream? No, none whatsoever, just like SQL doesn't care how the data is stored on the file. I mean, obviously the system that's implementing it does care, but all we require is the data has a schema. It might have a kind of document-oriented schema, for example, orders with nested line items inside them. SQL can handle that kind of data. Or even late schema, the kind of thing that drill does, is possible in this. So, yeah, there are as few restrictions on the format of these as on the format of data in a system like, say, drill. Yes?
So, if the input is a stream and the output is a stream, why do we need that time aspect? Why couldn't it be infinite? Like, group by without a specific time, it would be every time a new order comes in, a new grouping would be output.
Yeah, but the question was, if the input is a stream and the output is a stream, why do we need time constraints? If the question is what goes into that group, right? If we're grouping stuff that has within the same hour, that's fine. But if you want to group together all orders of product 100, you know, product 100 may have been, the first order may have been in 1990, and the last order of product 100 might be in the year 2037.
From the moment you started the query to the moment you interrupt the query, you would see.
Yeah. Well, time is up. So I'll be outside. I'm happy to take more questions. Thank you, everybody.